this is a bit this formula. So it's very easy to satisfy this formula. We'll have to set x2 to true, and at that point the entire thing becomes true. If x2 is false, then we can satisfy this one by setting x1 true, but this doesn't then help this one, which will remain false. So any truth assignment where x2 is true will be a satisfying truth assignment to this formula. So if we then go in and try to construct this graph, so we have the top node, which will go into, so this will be the x1 layer. I haven't talked about how many nodes you need to have on the layers, but it becomes fairly clear that it is a polynomial in the size of the satisfiability formula. You need sufficiently many to fit all the closed vertices in without trying to reuse vertices or something like that. But since there are only so many clauses, this can't really make the layers too long. So in fact, I will need 7 vertices for this particular case. But in principle, one can just grow the layers as one needs. So this is 5, 6, and 7. And then we should also be able to start out here. And then we're going to do another layer for x2, which also will get 7 vertices. Five, 6, and 7. And then we are able to go straight down. So if we have gotten to the left of the x1, we can go to the left of the x2, or we can go to the right of the x2. Out on the right here, we can go to the right, and we can go to the left. And then this is connected to the bottom vertex. So again, now we have just this little base case. However, this is quite sufficient just to see a couple of things, and that is how many Hamiltonian paths are there on this particular graph. There are 4 Hamiltonian paths. What you can do is one path is to down here, walk through this one, down here, walk through this one, and down here. This corresponds then to this note here, so we have the true direction, x1 being true and x2 being true. A second Hamiltonian path is to down here, to right, then we do down here, and the right to left, and out. This corresponds to x1 being true, x2 being false. Then we can do like so, so, x1 true, x1 false, x2 true. And then finally we can do this walk, which corresponds to x1 being false and x2 being false. So so far we only have the basic framework then for making sure that we can make variable assignments. Now we're going to add the clauses and show that these variable assignments will correspond directly to satisfying the clauses. So I think I'll move over on this side now. So we start with x1 or x2. And now it will get very messy because I will have to cross many edges across each other. So x1 true, which means that we want it to make it possible to visit this closed vertex if we are walking from the left to right on x1. That is on true assignments for x1. So we can do it like so. x2 true. So same thing. If we're walking left to right on x2, then we want to make it possible to visit this closed vertex. Like so. I'll have to be very careful here with the lines. So this is it for this closed vertex. So now we add the other closed vertex. Not x1 or x2. Man, that's an ugly one. So this one now in this case has a not x1, which means that working from right to left on this layer should be able to satisfy this clause, which means that if we are here, we're able to head into the clause, and we can head back out. And it has x2 true, so if we're working left to right on that layer, we should be able to satisfy this clause. So we are able to head from there to there, and from there to there. So, as noted, this is fairly messy, but we can now look at our 4 different Hamiltonian paths and see what these mean. We can, for the sake of it, start with unsatisfying ones. That is, the ones that where we worked from the right to the left on x2 should not be able to satisfy the formula. So if we start with what would correspond to x1 true, x2 false, what happens? So this should be this, then this walk. So we down here, and we start walking. Okay, we are able to visit now this close up here. So I guess I'll do a little bit. So we walk there, and we get here. And now we are able to visit this clause and get right back down here. So let's do so. There is never any reason not to. So we mark this one, mark this one, mark this one, mark this one. Okay, so this is an incoming edge. We can't do anything. We get here. Okay, so we have an outgoing edge here. So we could go into this. However, what would happen then is that we cannot take this edge back, because then we would revisit this vertex again, which is no good. And we can't really take this edge out either, because how are we ever going to get back up to this vertex if we were? So quite clearly, if we want to mark this vertex ever, then we need to mark it now. We have no possibility of actually heading into this close vertex. So we'll have to mark this, and I said we do x2 false. So we go down here, like so. Here again now, it's tempting to think we could visit this close vertex, but it's not possible because it's outgoing edges. This one already visited, this one already visited, so the only thing we can do is continue. Now we got here, and so this is now an edge up here. However, for one, we have already satisfied this clause, so we can't visit it no matter what. And second, we would actually end up back at the vertex that is already marked. So we are unfortunately done for, and the only thing we can really do is continue down here. However, this has left this close vertex now unmarked, as we would expect, because the truth assignment here, x1 true, satisfied this clause, but x2 false does not satisfy this one, and x1 true does not either. So we were unable to visit that particular vertex. So if we were to do x1 false, we would get a very similar case, but let's instead do one satisfying one now. There we go. I guess so. So let's do perhaps x1 false, x2 true. So we switch around this way. So this one should be okay, because it's enough that the x2 is true to actually satisfy all of it, though we will use the fact that x1 is false just for the sake of it. So we again start out here. x1 false should correspond then to do this walk. I forgot to erase one over here. Okay, so now we're able to visit this clause and get right back here. So there's no reason not to, though we don't really have to get this clause in this particular case. So we continue. So this one, again, is not really possible because we can't go back here. And if we were to go back down here, how would we ever mark this one? So we will have to continue on this layer. And now we're going to do x2 true, so we start from this direction. There we go, and now we have an opportunity to visit this one. We already did though, so it is no real help. But this is indicative of the fact that we have satisfied this particular clause in 2 ways this time. But we just continue to the right since it's already satisfied. And now we are able to go into this one, satisfying that, back out, and down. And there we have a Hamiltonian path. So hopefully this should seem reasonably clear now. We should still make an argument for why all of this works, but I think to some extent this example already makes the argument. Fortunately, my laptop has fallen asleep, so there might be a little bit of a cut here at some point. Last time it took a while. Okay, so it's actually working. Yeah, so we can still make a slightly more thorough argument for why this approach is correct. But I think it's fairly clear from the sketch exactly this property that you cannot skip around the layers as you please, and you will have to do this in a certain way. So if we have a variable assignment A for the satisfiability formula, then there exists a Hamiltonian path in the graph. And this is just basically finding this walk the way I illustrated. We have to start at the top, we have to end at the bottom, and we have no choice but to pass through the layers in one direction or the other as we go down. Choose to pass through the layers in the direction indicated by the truth assignment, and you will find that there will be a Hamiltonian path. We will be able to visit each clause vertex on the walk through the variable that satisfy that clause. So this is fine. Yeah, this really all there is to say about it. In the other direction is not much harder. Here one needs to be careful because one has to make a fairly stringent argument why you cannot skip layers. We will not really do this because basically the proof I don't think is more illustrative than the intuition. So must start at the top, must end at the bottom. It is in fact not possible to skip around. You will have to walk through the variable widgets all the way in one go. And since a Hamiltonian walk visits all vertices, it means it must visit all clauses, and it will visit clauses only when it has found a variable that satisfies the clause. And if all clauses are satisfied, then it's a satisfying truth assignment. So there is nothing much strange going on. So the conclusion, you can reduce satisfiability to Hamiltonian path, which means that Hamiltonian path is at least as hard as satisfiability. The proof that it is precisely within a polynomial bound as hard is fairly easy as well, but we skip that part and satisfy ourselves with this. So thank you for listening, everyone. Questions?